with the right hand side. So if we start with 2n plus 3 all squared, that's 2n plus 3 multiplied by itself. Then we need to subtract from this 3 lots of n minus 1 n plus 2. So let's expand this double bracket here first. 2n times 2n is 4n squared. 2n times 3 is plus 6n. 3 times 2n is also plus 6n, and 3 times 3 is plus 9. Now we come to this part here. The way we want to approach something like this is writing negative 3, then a large bracket. Then we'll expand the double bracket and write the result inside this large bracket. We need to be really careful here to make sure we don't make mistakes with signs. So we're going to start with n times n, which is n squared, n times 2, which is plus 2n, a negative 1 times n, which is negative 1n, and a negative 1 times a positive 2, so negative 2. Then we'll just simplify this part here, so we have 4n squared. If we add the two 6n's together, we get 12n, and then plus 9. But for this part here, we're now going to multiply that entire bracket through by negative 3. So it's negative 3 times n squared, or negative 3n squared, negative 3 times positive 2n, so negative 6n, negative 3 times negative n, and two negatives multiplied gives a positive, so positive 3n, and negative 3 multiplied by negative 2, so positive 6. We can now simplify by collecting like terms. So in n squared, we've got 4n squared minus 3n squared, which is 1n squared. We've got 12n minus 6n plus 3n, which is plus 9n. And then we have 9, add 6, which is 15. Now the right hand side for this example is a little bit different. We have a double bracket, but then we also have plus 1. If we look at this double bracket here and imagine expanding it, we'll get n squared plus 7n plus 2n, which will give us plus 9n, and then plus 7 times 2, which is 14. We just have a plus 15 rather than a plus 14, but that's why there's this plus 1 here. The best way to show this is rewrite what we have as n squared plus 9n plus 14, since we know that's what we'd get if we expanded the bracket, and then plus 1. You could almost think of this as unsimplifying the 15 into a 14 plus 1. We now know that this part here will factorize to give n plus 2 n plus 7, and then we have a plus 1 on the end. And that's the proof complete. We started with this here, which was our left-hand side, and then we ended up with this here, which was our right-hand side. In this next proof, it's going to specify that n is a positive integer with n greater than 1, and we're going to prove that this is a multiple of 12. So this is a very different type of proof. Let's talk about what it means to be a multiple of 12. The multiples of 12 are the numbers in the 12 times table. So if you multiply 12 by any integer, you'll get a multiple of 12. For example, 12 times 1 is 12, that's a multiple of 12. 12 times 5 is 60, that's a multiple of 12. In fact, 12 multiplied by any integer will give a multiple of 12. Since in this question we're told that n is an integer, we could replace the word integer here with n. So 12 times n, which is 12n, must also be a multiple of 12. In fact, 12 multiplied by 3n squared plus 2n plus 5 will also be a multiple of 12. This is because 3n squared plus 2n plus 5 must be an integer, and 12 multiplied by any integer will give you a multiple of 12. We're going to use this idea in this proof. So we're going to start with the expression we're given, and we're going to try and manipulate it so that it's a multiple of 12. So let's first of all expand these brackets. We've got n plus 4 all squared, which is n plus 4 times by itself, and then we need to subtract from this n minus 2 multiplied by itself. If we start with this first double bracket, we have n times n, n squared, n times 4, 4n, 4 times n, also 4n, and 4 times 4, 16. Then when we come to do the second bracket, just like the previous question, we're going to need to be careful with the signs here. We're going to write a negative, then a big bracket, then when we expand these two brackets, we'll put the result inside that bracket. So we'll do n times n, n squared, n times negative 2, negative 2n, negative 2 times n, negative 2n as well, and negative 2 times negative 2, positive 4. We can simplify this quadratic here, it will be n squared plus 8n plus 16, and then we need to expand out this bracket. Since there's no number in front of the bracket, you could think of that number as being negative 1. So negative 1 times n squared is negative n squared, negative 1 times negative 2n is positive 2n, the same for the next term, and negative 1 multiplied by positive 4 is negative 4. Now we can go ahead and simplify. We have n squared subtract n squared, which is actually 0. Then we have 8n plus 2n, which is 12n, and then 16 subtract 4, which is plus 12. Now this is not surprising that we've ended up with 12s here, since we're trying to show it was a multiple of 12. To do this properly, you now need to factorize this expression. So we're going to factorize out a 12. So it'll be 12 lots of n plus 1. Since when you expand 12n plus 1, you get 12n plus 12. Now we know in this question that n is an integer, so this part here, n plus 1, must also be an integer. Therefore we've got 12 multiplied by some integer, which we know must be a multiple of 12. So we can finish this proof by writing down a sentence. n plus 1 is an integer, so 12 lots of n plus 1 must be a multiple of 12. Let's try another example a bit like this one. So once again we have n being a positive integer, but this time we're going to prove that this is a multiple of 10. So let's take the expression, and if we start with the 3n plus 2 all squared, that's 3n plus 2 multiplied by itself. Then we subtract from this 3n minus 2 multiplied by itself, and then we're also going to add 2 lots of 3n plus 5. So let's expand this bracket here first. 3n times 3n is 9n squared, 3n times 2 is plus 6n, 2 times 3n is also plus 6n, and 2 times 2 is 4. For this next bracket, we're going to do that idea again, where we write one big bracket and write the answer to that expansion inside it. This prevents us from making any errors with our signs. So we have 3n times 3n, which is 9n squared, 3n times negative 2, negative 6n, negative 2 times 3n, also negative 6n, and negative 2 times itself, which is positive 4. Then right at the end here, we have to expand this bracket, which we can do now. 2 times 3n is 6n, and 2 times 5 is 10. Next, if we simplify this quadratic here, we've got 9n squared, 6n plus 6n is 12n, and then plus 4. Then if we move on to this bracket here, we need to expand this out. Imagine there's a negative 1 at the front of the bracket. Negative 1 times 9n squared, negative 9n squared. Then we have plus 6n, subtract 4. And then of course we've got these two terms on the end as well, plus 6n plus 10. So we now need to simplify all of this. So we have 9n squared, subtract 9n squared, which is 0. And then we have 12n, plus 6n plus another 6n, which will give you 30n. And then we have 4, subtract 4, which would be 0, and then plus 10, which is plus 10. So remember in this question we were trying to show it was a multiple of 10 this time. To do this we need to factorize out a 10. So it'll be 10 lots of 3n plus 1, since 10 multiplied by 3n plus 1 is the same as 30n plus 10. So just like in the previous proof, since n is an integer, 3 lots of n plus 1 is also an integer. So we can finish this proof by writing 3n plus 1 is an integer, so 10 lots of 3n plus 1 is a multiple of 10. In this next proof, n will be a positive integer again, and we're going to prove that this is even. So what do we mean by an even number? Well, even numbers are 0, 2, 4, 6, 8, 10, and so on. In fact, the negative versions of these are also even, so negative 2, negative 4, negative 6, and so on. Notice how the even numbers here are just the numbers in the 2 times table. So to show a number is even, we just need to show that it's a multiple of 2. So just like we did for multiples of 12 or 10, we're going to show that this is a multiple of 2, which is therefore even. So let's take this expression, and we're going to show that it's a multiple of 2. So we'll start by expanding these brackets here. N times n is n squared, n times negative 2, negative 2n, 2 times n is 2n, and 2 times negative 2 is negative 4. Then for this bracket, we have n times n, which is n squared, and n times 6, which is 6n. Then if we do some simplifying, we have n squared plus n squared, which is 2n squared. We have negative 2n plus 2n, which would be 0, and then plus 6n, so just plus 6n. And there's only one constant here, negative 4. So we're trying to show that this is even by showing it's a multiple of 2. So we need to factorize out a 2, and we can now do that. So this would be 2 lots of n squared to get the 2n squared, 3n to get the 6n, and negative 2 to get the negative 4. So just like the last two proofs, we can now write a statement. N squared plus 3n minus 2 must be an integer, which means that 2 lots of that is a multiple of 2. But we know that a multiple of 2 also shows that the number is even. And that's the proof complete. What about if instead we had to show that a number was odd, like this one here? By odd numbers, we mean the numbers 1, 3, 5, 7, 9, 11, and so on, and also the negative ones, negative 1, negative 3, and so on. Notice how all of the odd numbers are just one more than an even. For instance, the number 1 is one more than 0, which was even. The number 3 is 1 more than 2, which is even. The number 5 is 1 more than 4, which is even. So all odd numbers are just 1 more than an even number. So to show a number is odd, we need to show it is 1 more than an even. Let's now try this question with this in mind. So let's take the expression, and we'll start with this double bracket here, which is 2n minus 3 multiplied by itself. And then we also have plus 4 lots of n minus 2. So let's expand this bracket. 2n times 2n is 4n squared. 2n times negative 3, negative 6n. Negative 3 times 2n is also negative 6n. And negative 3 multiplied by negative 3, positive 9. For the single bracket, we've got 4 times n